Hi, thank you for watching this video. In this video, I'm going to talk about the problem of file updates under random or arbitrary insertions and deletions. The work is motivated by communication problem in cloud computing. For example, in file backup systems like Dropbox, the user has files stored in his own computer, at the Dropbox server, and also in his other devices. When the user edits his file at his own computer, there is some transmission of information to update the Dropbox server. Also, the server also needs to transmit some information to update the user's other devices. The goal of our work is for throughput and computationally efficient communication schemes to update files. From this problem, we have our communication model. Here, X denotes the pre-added source sequence, hence called the press. Y denotes the post-added source sequence, hence called the process. The process Y is obtained from the press X through some insertion-deletion process. The encoder takes in X and Y as input and output some transmission to the decoder. The decoder receives the transmission and it has access to the press X as source information, as site information. And the decoder hopes to reconstruct the process Y prime. In our work, we studied two different models for the insertion-deletion process, and we are going to talk about them in more detail. The first indel process we studied is a random pre-added sequence and left-to-right random indel process. Hence, we refer to it as the random model. In this model, the added process is modeled as a Markov chain with three states: the insertion state, the deletion state, and the no operation state. We here present an example of how a pre-added sequence, after processing the added pattern, converts to a post-added sequence. We use this example in our paper to explain different ideas. So the process starts from the beginning of the sequence. When the added is no operation, the cursor moves forward by one position. When the added is an insertion added, the process inserts a symbol drawn randomly, uniformly at random from the source alphabet, hence lengthen the sequence by 1. When the added is a deletion added, the symbol at the cursor is deleted, hence shorten the sequence by 1. So on and so forth until the end of the sequence. The other model we study is the arbitrary pre-added source sequence arbitrary induced process model. In this model, the source sequence can be any length n sequence from constructed by symbols from the source alphabet. And for the induced process, the insertions can insert arbitrary symbol from the source alphabet, and the deletions can delete arbitrary symbols in the sequence. And also, the insertions and deletions can occur in arbitrary order. The only constraint here is that in total, there are at most epsilon n insertions and delta n deletions. Now we come back to the communication model. And for the two different models for the induced process, we have different metrics. For the random model, we care about average communication complexity and allow small error decodability. While for the arbitrary model, we care about worst-case communication complexity and allow zero error decodability. For both models, we come up with information theoretic alphabet-sized lower bounds, and indeed, this is the major contribution of our work. We also propose computationally efficient achievability schemes, and our inner and outer bounds nearly match up to first-order terms. We will present the bounds in more detail later. There are two lines of related works. One is insertion-deletion channels. The similarity is that our induced process model can also be viewed as an insertion-deletion channel model. However, the motivation of these two problems differs. For our file updating problem, the source statistic for X is given. The problem is similar as Slavin-Wolf source coding problem with decoder side information, where the decoder side information is the old file X. Hence, the problem is to minimize the entropy of Y given X. However, for the insertion-deletion channel, the goal is to find the channel capacity. Hence, equivalently, it's to maximize the mutual information between X and Y, and it's over all possible statistics for X. The other line of related works is file synchronization problem. There are two main differences between file update problem and file sync problem. In our file update problem, the encoder has access to both files, and the decoder has only the old file. And the decoder wants to update the old file to the new file. While in the file sync problem, the encoder and decoder each has one version of the file, and either one of them wants to learn the other file, or they both want to recover the other file. The other difference is that in most works in file synchronization problem, they allow two-way communication. However, while in our file updating problem, it's one-way communication. This is a table summarizing some prior work about file synchronization problem and file update problem. We are not going to talk about the details of this table in this video. However, we just want to compare with the closest work to our work. In the work by Ma, Ranchanjan, and Xie, they also focus on finding the explicit information theoretic lower bound for the random edit model. The difference is that in their work, the alphabet size is binary, while in our work, the alphabet size is arbitrary, and our lower bound is alphabet sized. The other difference is that in their work, the edit operation is only deletion, while in our work, we allow both insertions and deletions, and this adds to the complexity of our analysis. For some discussions about other prior works, we refer to our paper. Here we show the main results of our work. For both the random model and the arbitrary model, we have lower bounds and achievable rates for the communication rate. The highlight parts are the terms up to the first order terms. And we can see our lower bounds and achievable rates nearly match. For example, in the random model, the first three terms match. The only difference is in the term epsilon plus delta times some constant. And this constant is only determined by, only depends on the alphabet size. However, the constant is maximized when the alphabet is binary, where hence C2 is approximately 1.29. Moreover, as the alphabet size increases, this constant decreases and converges to 0. Hence, when the alphabet size grows, our inner and outer bound match closer. For the arbitrary model, also the terms up to first order nearly match. The proof of the lower bound for the random model is the most technically challenging part in our work. We built non-trivially on Canoria and Montanari's work on deletion channel. In this figure, we show all the important random variables in our proof and their dependency. In the beginning, only the pre-added, the press X and the added pattern are given. The process Y is obtained by operating the added pattern on the press X. Hence, Y is a deterministic function of X and E. However, X and Y are in general difficult to align. So we carefully perturb the added pattern to a typicalized edit pattern E hat by eliminating some dense edits. And whether the edit is dense or not is depending on checking the number of edits in the runs in the press X. Hence, E hat is also a deterministic function of X and E. After obtaining the typicalized edit pattern, we can process it on the press X and to obtain a typicalized process Y hat. There are also some other important internal variables for our proof. Here we show two important internal variables. The first one is E hat complement, which stores the eliminated edits. Hence, the original edit pattern is in some sense the union of the typicalized edit pattern E hat and the eliminated edits E hat complement. The other important internal variable is this global alignment variable. The reason why we perturb E to E hat is that after this, the X and the Y hat can be almost aligned, but still we need some extra information to align X and Y hat, and this A sub X Y hat is the extra information we need to align X and Y hat. This is the flowchart of the proof. The first step is similar as the converse for Schleffen-Wolff converse. It shows that the number of bits the encoder needs to send merely equals the entropy, conditional entropy of Y given X. The difference from the proof in the Schleffen-Wolff converse is in the finals inequality. We need to modify finals inequality a little bit because we allow insertion in our model. The length of Y can be unbounded. The next equality shows that this conditional entropy equals the entropy of the edit pattern minus the conditional entropy of E given X and Y. This equality is because in our model, X and E are independent, and also Y is a deterministic function of X and E. The intuition of this equality is that to describe the information in Y given X, one almost need to describe the edit pattern. However, to describe the explicit edit pattern is redundant. For example, if X is 3 zeros, Y is 2 zeros, one doesn't need to tell explicitly which zero got deleted from X to Y. Hence, this conditional entropy H of E given X, Y is the redundant information in E given in the edit pattern given the sequences X and Y. And this is called the nature's secret in Ma Renchenzhen and Shes paper. We also use this term in our paper. In general, this nature secret is difficult to calculate. Because here the process is not a memoryless one. It's a process with memory. Hence, X and Y are in general difficult to align. To bound this term, we have mentioned in the previous slides that we perturb the edit pattern to some typicalized edit pattern. And we show in our paper that for the typicalized edit pattern, the nature secret can be bounded through some case analysis and alignment module. This case analysis and alignment module is the most complicated idea in our work, and we will show it more detailedly in the coming video. Besides the implication that the typicalized nature secret can be bounded through this alignment module analysis, another implication is that the nature secret is close to the typicalized nature secret. And this is through finding this two pair of relations. Here, the relation means that E, X, and Y is a deterministic function of E hat, X, Y hat, and E complement. Also, E hat, X, Y hat is a deterministic function of E, X, Y, and E hat complement. For these two pairs, X, Y, and X, Y hat, we have similar relation, but we need slightly more information over the arrow. These two pair of relations are also implication from the alignment module, and we will talk about it more detail in other video, and the detail is also presented in the full version of our paper. Hence, through the two pair of relations, we can bound the difference between nature secret and the typicalized nature secret by 2 times entropy of E hat complement plus the entropy of the global alignment information. And these two entropy can also be bounded. Hence, we can derive our lower bound for the random model. Next, we talk about the lower bound for the arbitrary model. We denote the post-edit set of some press X to be the set of all sequences that may be obtained from X through the index process. Hence, for zero-error decodability, we need log of the size of post-edit set, such many bits, to be communicated. Hence, to find a good lower bound, we need to find a press X with large post-edit set. The press X we found is the sequences constructed by alternating two symbols, such as the sequence 010101. The properties of this sequence is that the number of this kind of sequence has the largest possible number of rungs, which is n in this case. And also the sequence is constructed by from list many symbols from the alphabet. So this kind of sequence is only constructed by 2 symbols from the alphabet. The next step is that we consider a subset of all possible edit patterns, where the edit patterns in this subset all leads to different process after processing on the pre-S. This subset of edit patterns has 3 constraints. The first constraint is that all the deletions precede all the insertions. Then for the delta n deletions, it may delete any symbols which are not pairwise contiguous. So it cannot delete 2 symbols next to each other. For the epsilon n insertions, it may insert any symbol other than the 2 symbols which constructed the sequence. We can calculate exactly the size of this subset. And because the edit patterns in this subset all leads to different process, this number is a lower bound for the number of all different process. The log of this number will give a lower bound for the arbitrary model. Here is the triviality of our work. Because the major contribution of our work is in coming up with the information theoretic lower bounds, we talk about achievability briefly in this video. The scheme is just by taking in X and Y as input, the encoder using a dynamic program on X and Y to find an edit pattern with least number of edits. And then the encoder uses entropy coding to compress the edit pattern output by dp. Note that indeed using dp to find the edit distance is well known in literature. Our contribution here is to show that the rates achieved by this scheme nearly match the lower bounds. And also the computation complexity of this scheme is tractable. We show the main results again just to compare the lower bounds and the achievable rates. Thank you for watching this video.